All right, y'all. So today I'm going to be talking about Coulombic forces and effective nuclear charge. You can see that right here at the top. So basically, I'm going to start off from the beginning. I'm going to start with Coulombic forces because you need a good understanding in Coulombic forces to kind of understand where effective nuclear charge and almost every other trend actually comes from. So as we start Coulombic forces, let me go ahead and write that here. Coulombic forces. I may call them by a different name, that name being electrostatic interactions. So either way, they're the same thing. So let's go into what they are. So the first thing is they are forces felt between charged particles. So any particle with a charge can have Coulombic forces. Right now, we're generally thinking about protons and I should have charge in there. Protons and electrons. That's what we're going to be mainly talking about when we talk about charged particles. Um, and so we generally have a positive and a negative charge. Most people understand that when you put these two together, they attract. Now we may also have a positive and a positive charge. In that case, they will repel. And lastly, we can do a, oh, whoops, my bad. A negative and a negative charge. And that will also repel. So you can think of these similar to magnets. When you have the North Pole and the North Pole, it repels, or South Pole and South Pole, it repels. But when you have opposites, they attract. So here we kind of have opposites attract and same repel. And while we may have opposites attract and the same repel, the overall force that they'll feel, whether that force is pulling them together or, pushing them together, pulling them apart, is judged by an equation known as Coulomb's law. Coulomb's law basically says that the force felt by any one charge on another is equal to some constant k times the charge times the magnitude of charge 1 times the magnitude of charge 2 all over the distance between them squared. So I'll go ahead and write these out. I'll use a different color. Overall force constant. So in science equations, we have a lot of constants. You can usually think of, oh, now I'm blanking on literally every constant ever. We have Planck's constant, which we use when we're talking about the frequency of light. A constant that you use quite often in math is pi. The pi is a constant number that you can use. It's not judged by variables. It just is 3.14, etc. Then we have Q1 and Q2, and these are the charges of the particles. And then last we have R squared, which R is the distance between particles. And I'm going to kind of highlight this section right here, the Q1, Q2 over R squared, because that's all we'll really be talking about. Basically, what this little thing says is that if we look at the way the charge interacts on the force, if we look at the way that whole thing interacts on the force, if we just bring those down, F equals Q1, Q2 over R squared. So if we just look at that part minus the constant, because it kind of gets things confusing, we can see that these things are on the top and they're multiplied. So anything that happens to one of them will happen to the other, like in math. If I take Q1 and then multiply it by 2. So if I take Q1 and multiply it by 2, then the force will also be multiplied by 2. Basically, like any math equation, whatever you do on one side, you do on the other. So things get a little more confusing when you talk about distance down here. So the problem is distance is squared. Whoops. Distance is squared, which means whatever happens to the distance. So if R now becomes 2R, well, what was once R squared is now 2R squared, which that's 4R squared. So whatever happens at a squared magnitude, which means force, instead of being divided by 2, even though distance doubled, the force is 1/4. So I'm just going to show this real quick. If we just change the charge, so if we have a plus, I'm going to set up 3 examples, 1, 2, and 3. If we have 2 pluses versus a plus. So if we have a plus and minus some distance away, I'll do all my forces in green. So this will be some force because we have some distance. If we go ahead and take that same force, or we take that same distance, we keep it. The force here, I'm actually going to go ahead and move some things around. Who's back? So this will be equal to some force. This, because we have 2 times the charge, this will be 2F. However, the problem comes here when we go ahead and double the distance. That's 2D. The force is actually affected by 4 times that amount, or actually 1/4. So that's the main thing I want to really get through. Changing the distance greatly changes the force, while changing the charge only changes the force the same amount. So this is pretty much all that Coulomb's law is. It doesn't matter if these are positive and positive, positive and negative, negative and negative, because then that just tells us whether the force is bringing them together or pulling them apart. It doesn't matter either way. So with that, we're going to move on to the effective nuclear charge, which now that we know Coulomb's law, will make hopefully a lot of sense. So the effective nuclear charge. And this basically can be stated as the charge an electron feels from the nucleus. And by the way, when we talk about the nucleus, we really only mean the protons in the nucleus, because the other particles, the neutrons, do absolutely nothing because they're neutral. And Coulombic forces or electrostatic interactions only work on things with forces or with charges. So real quickly, let's go over the equation for it because we got this handy equation. We have Z effective, which is just the effective nuclear charge, is equal to Z, and that's the number of protons, which, by the way, the number of protons is equal to the charge of the nucleus, because once again, all the protons are in the nucleus, the neutrons don't have any charge, therefore the full charge is Z. And then we're going to say minus S. Now, S is kind of the weirder part of this. S is the shielding. And the thing with shielding is it's not so much electrons blocking the nuclear charge, like that positive, but it's the fact that while the electrons on the outside feel that strong force to go in, the electrons between the outer electrons are also saying, get out of here, because they're negatively charged. They're also repelling. They're trying to push away. So shielding is more the repelling force of inner electrons. All right. So we have all this set up. So the final thing to go do is an actual model. Now we're going to be using Bohr models. And let's go ahead and look at sodium. You know what? Actually, no, I did a lot of sodium problems in class. Let's look at magnesium. Magnesium has 12 protons and 12 electrons. So I'm going to go ahead and draw that here. But instead of writing the nucleus by doing bubbles or writing Mg, no, I'm not going to do that. I'm actually going to go ahead and erase all that. All I care about is the charge of the nucleus. All I care about is this charge of the nucleus. And so 12 protons is actually going to create a plus 12 charge. So that's my nucleus. Right here. Nucleus. All right, so now I'm going to go ahead and make my electrons. I'm going to try and make these nice rings. All right, so I've got that. I'm going to go ahead and erase this nucleus label now. And as I make my electrons, we know that we have 12. So I'm going to go ahead and fill this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And a quick thing I want to address here, because I'm not sure if we've really made the connection, is that if we remember from the Bohr model, this is n equals 1, n equals 2, n equals 3, and these are our energy levels. Now, because there are energy levels, we actually know how many electrons they can hold. Because something else you might remember is if we look at our energy levels, 1, 2, 3, 4, 5, 6, 7, like the rows of the periodic table. If you look at our energy levels, energy level 1 only has the 1s orbital. Energy level 2 has the 2s and the 2p. 3 has 3s, 3p, 3d. 4 has 4s, 4p, 4d, and 4f. And 5s, 5p, 5d, 5f. And again, f is all we have, so it's just going to go down to 7s, 7p, 7d, 7f. And this is significant because the s orbital only holds 2 electrons. The s orbital, again, has 2, but the p orbital, which consists of 3 p orbitals, So the p sublevel is 3p orbitals. Each one holds 2. That's 2, 4, 6. So we can hold 8 electrons. Now we have our 8 plus the d orbital. The d orbital is 5d orbitals. So the d sublevel holds the 5d orbitals. And each one of those holds 2. So that's another 10. So it's 2 plus 6 plus 10, which equals 18. And lastly, we now have our 18 plus the f sublevel. There are 7 f orbitals. Each of those hold 2. So that's another 14. So it's 2 plus 6 plus 10 plus 14 for a grand total of 32 all the way down. So as we draw our Bohr models, each increasing ring can hold more electrons up to the 4th, where they just stay at 32. By the way, that's how I got the electrons. So sorry about that tangent. We're gonna kind of resume where we left off. So let me just go ahead and kind of recopy this. We're gonna start a new page so I can start fresh. Anyways, so let's go ahead and look at our Z effective. Well, our Z effective is gonna be the number of protons, 12, minus the shielding from the electrons. We can literally, there's a bunch of complex ways to calculate shielding, but there's a simple way to estimate it. A general estimate of shielding is literally by just taking the number of inner electrons. What I mean by inner electrons is any electron in an energy level below the one you're looking at. So this is any electron in an energy level lower than the electron we are looking at. So right now we'll go ahead and look at this outermost electron. And so for the shielding, we have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our equation becomes pretty simple. It's just going to be 12 minus 10, which equals plus 2. So the effective nuclear charge of the magnesium nucleus on the outermost electron is plus 2. So I'll write that. The effective nuclear charge of the magnesium nucleus on its outermost electron is plus 2. And basically that's how we do any of these problems. A couple things to note. Following this logic, anything in the same row seems to have the same effective nuclear charge. So if we look at beryllium, so we'll look at beryllium, which is got 4 protons and 4 electrons. So I'll go ahead and draw that, plus 4. One, two, 1, 2. So if we do our quick equation, Z effective, and we're looking once again at one of these outermost electrons, it really doesn't matter which one, is going to be equal to 4 minus 2. And so you may think, oh, plus 2. They have the same effective nuclear charge. Well, in our estimation, yes. However, you may remember that I said shielding is an estimation. And it turns out that these inner electrons shield much less than the further out inner electrons. And then one more consideration is distance. If I go ahead and let me go ahead and duplicate our magnesium atom once more. Duplicate. And I'm actually going to duplicate it again, because this time I'm going to take away the outer stuff that makes this magnesium. Oops, that one was one too far. Oh no. You know what? Y'all get the point. I'm not going to erase all that. And I'm going to make this one beryllium. And if I look at this, we can see that the electrons on the outside, we'll say distance of beryllium, distance magnesium. And if we compare these distances, the electrons on beryllium, the magnesium, is a larger distance than the beryllium. And because it's a larger distance, we know from Coulomb's law up at the top here, we know from Coulomb's law that distance plays a much greater role than the addition of more charge. The addition of more charge may have some increase related to that addition. However, the distance has a squared decrease to that. So as we increase the distance, the force is decreased by a squared amount. In our case, 2 to 4, doubled becomes 4 times. So with that said, overall, if we look at finally last thing, the trend of effective nuclear charge increases. I'll just say Z effective so I don't have to write it. So the effective nuclear charge increases across. That's all I have for you today. So thank you very much for bearing with me, and I hope this helped.